Hello, I am Mustafizur Rahman. I will present our paper accepted in Semantic Web Application Track ACC 2020 entitled as Representation Learning for Entity Type Ranking. My co-authors are Professor Atsuhiro Takasu and Professor Gianluca Di Martini. Okay, let's move to the details of this presentation. The type of an entity is a key piece of information to understand what an entity is and how it relates to other entities mentioned in a document. Type information plays an important role in knowledge graph or knowledge bases as website user expectations increase the effective use of knowledge graph to generate correct search engine result pages become very essential. Entities relevant types can be shown in the search engine result pages to recommend more meaningful facts for entity centric queries, which will increase user engagement that we believe. Entity types carry information about the different roles of an entity. In this slide, we can see some type information of a specific entity. From those type information, we can understand the characteristics of this specific entity. As an example, we can assume that this entity actually a person. He or she is a politician, also known as actor, maybe, and so on. Actually, those types actually are associated with the entity Donald Trump. As you can notice, the entities are often associated with several types, and selecting the most relevant types or answer a query about a particular entity is challenging while there is no type ranking. Okay. In this slide, we formally define our task and the input and the output and the evaluation part. This task is motivated by the fact that in current knowledge graphs, entities are sometimes associated with too much information, which human user cannot process quickly. Some nodes in a knowledge graph can have hundreds or thousands of incoming or outgoing edges describing the entities they represent. Among all the information that can be attached to entities, type information is vital as it defines what the entities are. For this reason, we tackle a task which also can be seen as entity summarization that we call entity type ranking. In our problem, input is a knowledge graph. You can see in the slide. Input is a knowledge graph G with type info triples and an entity E. Traditionally, knowledge graph contains relational triples, but in this paper, we introduce a relevance property and connect the entity and its respective types with this relevance property. We'll discuss in more details in upcoming slides. And the output of our system is a ranked list of given entity E. This is the ranked list of the types of an entity, as you can see in the right corner of the text. And we evaluated our system with very well-known evaluation metrics. Okay, let's go to the related work. T rank is the most related work with this paper. T rank introduced different approaches to deal with the problem and used crowdsourced relevant judgment on real dataset to experimentally evaluate the proposed ranking methods. Author evaluated several type hierarchy and graph-based approaches that exploit both schema and instance relation. You can see some here like frequency, wiki link, or same as, and uh, here you can see some other approaches defined by them. As T-Rank defined many approaches, author also combined these approaches to retrieve the best types by using decision trees and linear regression. These entity type ranking approaches are different than the approach we present in this paper. While we aim at solving the same problems, the same task. For this reason, we evaluated our models and compared our results over the same dataset and using the same grand truth data. Okay. Let's discuss the general terms we will be using throughout this presentation. At first, embedding. An embedding is a relatively low dimensional space into which we can translate high dimensional vectors. We all know that. So the idea is also same for knowledge graph embedding. We know that knowledge graph contains facts about real world entities in the form of triples. You can see an illustration of a knowledge graph in the picture in the right, where node represent the entities and the age represent the relation between the entities. Okay. In this work, we address the entity type ranking problem by means of knowledge graph embedding models. In our work, we show that entity type ranking can be seen as a special case of knowledge completion problem. So, um, we had to construct a knowledge graph which also contains entity type information. Traditionally, a knowledge graph contains relational triples or fact. I already mentioned it. We introduce another property. We are calling it relevance to connect entities with their most relevant types. An entity type can be considered as distant item or characteristics, such an assumption help us to define the type ranking problem using knowledge graph embedding. Crowdsourced judgment between an entity and entity type is encoded by a special property called relevance, as I mentioned. You can see in the picture the bubbles represent the types and they are connected via age relevance. I will back to the knowledge graph construction process in a later slide. But the whole idea of knowledge graph creation in these particular problems look like this slide. Let's go to the details of our models. Here we introduce some modules, namely structure embedding and probability embedding and combined approach. We are calling it RLT rank. Structure embedding uh, interpret a relationship as the translation from the head entity to tail entity to characterize the structured information. We exploited translation distance based model in this particular case. Probabilistic embedding models define a conditional probability on triples. We'll see the details in later slides. RLT rank combine the structure embedding and the probabilistic embedding models and learn the embeddings jointly. Okay. As we mentioned, we employed translation distance based models. We adopt three popular embedding models. I'm sure you know the names: Trans E, Trans H, and Trans R. For our structure embedding module. In trans E, we translate the head and relation vector to tail vector. As you can see in the picture, how we realize the type ranking problem by using trans E. Uh, Here we consider the relevance property as a relation. The scoring function, uh, the equation of the scoring function, you can see at the bottom of that transit picture, and you can get a clear idea of what we actually did. And trans H represent the relation by hyperlines in the knowledge graph embedding. This model projects entities on the hyperline corresponding to a relation is which is different than which trans C. Similar to trans C, we can use trans H to our problem. We use the same scoring function as trans H. You can see in the picture. So we just introduce the a new relation, and the whole process is almost same. Okay, we know that Transy has some flaws in representing one to many, many to one, and many to many relations. Transr address the flaws of Transy, but in a slightly different way than TransH. Transr considers separate embedding spaces for entities and relations. The assumption is that entities and relation are completely different type of objects. So they should not be in the same vector space. According to the picture, the projection matrix M rel project the entity and entity types to the relevant space and calculate the scores of the triples. There are other knowledge graph embedding models like complex and convolutional network based models like conv, now showing very promising results. So the question is why we didn't care about those models in our structure embedding module. Actually, in our data, we do not have any symmetric or transitive relations. The relational structure is very simple. The head is always an entity, and the tail is corresponding entity type. However, in bilinear models like complex, add overfitting, add more redundancy than translation distance mesh model does. For this reason, they can have an overfitting problem since the triple structure in a dataset is very straightforward. So only translation distance model have been employed as a structure embedding in our proposed RLT rank models. This slide shows how we train our model. Uh, as per training purposes, negative triples are also required. We randomly replace the heads and the tails of positive triples with our entities and types, respectively. You can see the equation, the objective training objective equation here. We define a margin-based loss function as objective, similar to other knowledge graph embedding models for training. Actually, uh, is is same for most of the models, and you can see how we prepare the negative sample. We show a equation here. Okay, and in probabilistic embedding model, we took the advantage of the probabilistic modeling of knowledge graphs. We define the conditional probability on triples, as you can see in the first equation. We kept the same scoring function here as in structure embedding to keep the model simple. Uh, in the final objective function, where LPE actually, the summation is over S, which is the set of all positive facts. Okay. Considering the structure embedding and probabilistic embedding models together, we learn the embedding factors jointly in RLT rank approach. LAC and LP are the loss functions for the structure embedding and the probabilistic embedding. We adopt stochastic gradient descent to optimize the above loss functions. Here, LAC could be trans E, trans H, or trans R model, as you already mentioned. The task is to rank a set of n entity types according to a specific entity. The core idea is to build a knowledge graph with existing relations in the knowledge graph and add entity and entity type pairs with relevance property to the knowledge graph together with our existing relations. Once this is done, the model learns the knowledge graph embedding, which includes all the triples as well as the relevance property triples. In the final stage, we rank the types considering the score of type input triples. It's a very simple idea. To evaluate the validity of our proposed approaches, we use the same dataset created by tree-rank authors. Data had been collected from the top news of each category from the New York Times website during the period of February 21 to March 7, 2013. The retrieve entities were then linked to DBpedia and attached to corresponding types available in the link open data. To collect the relevant judgment for entity and type pair, anonymous crowd workers have been involved. Crowd workers voted for each entity and entity type pair. Type relevance has been measured based on how many workers voted for that pair actually. The pairs without any vote are considered as irrelevant types. We created knowledge graph for the entity type ranking task based on the mentioned dataset on the table at the left. You can see, and you can see the statistics of the triples and entities on the table at the right, which we used for knowledge graph embedding models and our RLT rank approach. This is the very important slide for this presentation. Uh, in the mentioned dataset, we have entities with their associated types and relevant judgment. As I mentioned, entities of this dataset have been extracted from New York Times articles and later linked with DBpedia. We collected the related facts for those entities by leveraging DBpedia to create our knowledge graph. During the knowledge graph creation step, we only considered those triplets that are directly connected to the entities in our dataset. One entity can have a subject or object role in the considering factor triple, as we know. Uh, in order to select the most relevant properties of the knowledge graph construction, we select a subset of properties from the DBpedia ontology to create the knowledge graph by sorting them according to their frequency of occurrence for each entity. Okay, I will give you an example to make it clear. As an example, for the entity Tom Hanks, DBO stating, which is actually a relation, appears 51 times in DBpedia. We set a threshold of frequency to select the properties and included them in the knowledge graph we constructed. We add all the DBO properties where frequency is more than 10. In our dataset, entity and entity type pairs have been judged over 4 level of relevance score as you already seen in the last slide. Score 3 means that the pair counted as most relevant one, and the score 0 means not relevant at all. We only include the relevant types to the knowledge graph and filter out the entity and entity type pairs which have score 0 or score 1. The process might sound very complicated, but it's not very complicated one. Uh, Please refer to our paper if you have any confusion. Okay. In this slide, we report the experimental results. We marked the best results with a blue and red circle based on the method. You can see. As you can see, RLT rank models outperform the baseline models along with the AC models. AC means structure embedding models separately. For RL3 rank model, it captures both the structure and the probabilistic information of knowledge graph, and proposed RLT rank with trans E and trans H obtained better result compared to RLT rank with trans R. In the EO dataset, RLT rank achieved the good performance in RLT rank with trans E achieves the good performance in the MAP metric. In other dataset, RLT rank with trans H shows the best performance among you can see the red circles. We also observed that the embedding dimension of structure embedding models affect the performance of RLT rank models, the combined approach. Uh, Trans E achieved the best result with dimension size 40 for the dataset EO, while for other dataset, Trans H performed better with dimension size 50. We observed that for dimension size less than 50, the performance decreases gradually for all models in our 4 dataset. As you can see, the effect of the dimension size in the figure. Okay, we are almost at the end of this presentation. Um, in this slide, we'll discuss about our observations. RLT rank consists of two components, as we told you already, structure embedding model and probabilistic embedding model. We observed that structure embedding models contribute largely to the overall performances of the RLT rank approaches than P models. P means probabilistic embedding models. Some entities and types have very limited entry in the training data. In such cases, joint models show better result than the individual models. We also showed you the individual results in the testing phase. For this reason, we have analyzed the structure embedding models deeply. One very interesting observation is the result of trans R among the structure embedding models. Trans R showed promising result in the knowledge graph benchmark dataset. We know that compared to trans E or trans H, trans R is a more complex model than trans E and trans H, of course. Um, Over this type ranking dataset, trans R failed to pro, to project the entity and type relationships. In this study, we focused on the relevance relation only. Trans H obtained very good results for relevance relationship, but for other existing relations in our constructed knowledge graph dataset, the performance of trans R is satisfactory. That we can say. One assumption that explains this result is that with more data of relevance relation property, transfer may show better type ranking performances. One of the drawback of using translation based model is the need to tune hyperparameters. And in future, we want to analyze entities behavioral pattern, considering the change of entity types over time. That's the plan for the future. Okay. uh, Here are the references of this presentation. Okay, please check our paper or contact us if you have any queries. uh, Thank you for viewing our presentation.